Okay, so good morning to everyone. Now, in the previous class, we have discussed about the how the direct mapping can be done in the cache replacement policies. We have seen about the cache mapping technique. So between this, the three cache mapping techniques are present. That is the direct mapping, set associative mapping, and the k-way set associative mapping. Total three cache cache mapping has there, and among them we have discussed in the previous class about the direct mapping. Now there is the advantage and disadvantage of this direct mapping. Now first we will discuss about the advantage, then we will discuss the disadvantage of direct mapping. Now first advantage is what? This method is simple and searching is very much easy. So to find any block in the cache, if CPU wants some block that is present in the cache and CPU wants that block to execute, so it is very much easy to search and also execute it. So we have already seen that for our this in the our total physical memory, or we can say our memory, there is the physical address which is generated, and that physical address is if in the main memory, then our physical address is total 7 bits. Physical address is total 7 bits because we have used 128 words, that the memory is capable of storing 128 words, or we can say 128 bytes. This is the capable of storing 128 bytes data in the main memory. So to represent this 128, how many bits is required? We have required 2 to the power 7. That means 7 bits is required. So that's why the physical address will be the length of 7 bits. And among these 7 bits, there will be the block offset. So the size of the block. So we have seen in our example that the size of the block is what? That the block is particularly capable of storing 4 words. So 4 words means what? 4 bytes. That means to represent the 4 bytes, how many bits are required? So 4 bytes is 2 to the power 2. So that's why that means 2 bits is required. So block offset, the block, or we can say the block size. So to represent the block size, we require 2 bytes. So among this, if 2 bytes is required, it is the block offset. Then how many bits will be remaining? So 7 minus 2, 5 bits. So this 5 bits will represent the block number. Now, if you see 2 to the, this 5 means what? 2 to the power 5. That means 32. That means 32. So you can match with this example, because 0 to 31 block number should be present. That's why that means what? That means we require total 5 bits. We require total 5 bits to represent the block number. So this is the physical address. This is the physical address in the RAM. Now, when this block will move into the cache, that means the block will be moved into the cache. In that time, this block number will be divided into 2 parts. This block number will be divided into 2 parts, because we know that this block offset will be same, because the size of the block and the line equal to the block size. So in particular line, there will see also that a particular block should be present in particular time, a block should be present in the line. So that means in the block there is 4 words present. So in the line also, in a particular moment, 4 words will be present. So that's why the block offset will be same. The block offset will be same, but the block number will be divided into 2 parts. This block number, that is we get, that is 5. So this 5 will be divided into 2 parts. What are the 2 parts? Now, if you see, there is what? There is in our cache. In our cache, there is block offset will be same. That means it will be 2 bits. Now we have one thing, that is the in our cache, that is the line number. So if you remember, in our cache, that we said that it is of 16 words. Our cache length is 16 words, and we have divided our cache. We have divided our cache into 4 lines. That means that is L0, then L1, then L2, then L3. These 3 ways we have this total 4. So that means the 4 line should be present in our cache, because we are considering that at a particular moment in line, there will be a block present. Now inside the block, how many words are present? 4 words are present. So that means 16 divided by 4. So our total number of lines should be what? The total number of lines should be 4. So that's why from L0 to L3, total 4 lines are present in our cache. That if we take 16 words, that our cache is capable of storing 16 words or 16 bytes. That means the total number of line present in our cache should be 4 from L0 to L3. Now to represent this 4, how many bits are required to represent this 4? To represent this 4, we require 2 to the power 2 bits. That means total 2 bits are required. So one another field will be there, that is the line number. So the line number should be how many bits? The line number should be 2 bits. The 2 bits data should be the line number. And that means what? Our total length is 7. So among them, the line number will be what? The line number is our 2 bits. And remaining bit, the remaining bit we called as the tag. In our cache, the remaining bit is called as the tag bit. So the total our length will be what? It will be the 7, our 7 bits, but among them 2 bits will be for the offset, 2 bits is for the line number. So how we get that the 2 bits of line number? From here, because we have 4 lines. So to represent the 4, we have required 2 to the power 2. That means 2 bits is required. So our line number will be 2 bits. And the remaining is what? And the remaining will be our tag bit. So 7 minus 4, that is 3, and this 3 is the tag bit. Now what is the tag bit? Now we able to know that line, what is the line number, what is the block offset, but what is the purpose of this tag bit? Now the tag bit is what it specifies. We have said that in a cache, and in there is cache, this cache is divided into line number. So at that particular moment, in a particular our line, which block should be present? That means if we take the example, that means in L0, which block should be present in L0? B0 block can be able to present. That means we can use the formula K mod N. K mod N we will use, and if we use then K mod N, then from there we can find that block 0 should be present in the line number 0. Then block 1 should be present in the line number 1. Block 2 should be present in the line number 2. Block 3 should be present in the line number 3. Then block 4 again should be present in the line number 4. Then block 8 can also be capable of it is of there in the line number 0. Then block like this, block 12, block 16, then block 20, block 24, block 28, like this. Then that means what? This block is capable. This block is what? This block will come only in the line number 0. Other than line number 0, if there is the space available also, then that time also this block is not came in the another line, because through K mod N, this formula says that only in the block number 0 should be present in the line number 0, and block 4 should be present in the line number 0, block 8 should be present in the line number 0, but B1 is block number 1, then block number 5, then block number 9, these blocks will be present in the line number 1. So that means many blocks, this B0, B4, B8, B12, this all blocks can be present in the line number 0. But at a time, which block should be present in that particular line? Which block should be present? Like if this tag bit specifies that means among B0, B4, B8, let's say B0 is present at that particular time in the block, because all the blocks cannot be present in the same time. Particular time, only one block should be present. So that's why this tag bit specify which block should be present at that particular time among B0, B4, B8, which block should be present at that particular moment in the line number 0. So this specifies the tag bit, and this is why the tag bit is used. Okay, so now let's say our CPU generates an address. Let's say this is the address. The CPU generates an address. So in this address is what 1, 2, 3, 4, 5, 6, 7. So that means total our this is our address. This address is generated by a CPU. Now this address has a tag bit, and for all the cache there is 1, 2, 3, 4. That means total 4 lines are present in the cache, and this 4 line, each line has a tag. Each line has a tag present. Now this tag of this cache and this tag of the address will be compared. Now if comparing the tag bit of the cache with CPU generated address tag, that means the address CPU generated address tag will be compared with the tag of the cache. And if CPU generated address tag and the tag bit of the cache is matched, if the cache is matched, like let's say this tag bits and this tag bits, 2 tag bits are matched, that means our the CPU required, the CPU, which block CPU is required is present in our cache. That's why these are matched. If these are matched, then that means the block CPU is wanting or CPU wants, that is present at that particular moment in our cache. Then we can say that the cache hit occurred. That means which CPU is finding the, we can say the finding, the CPU is finding that particular block or the particular word, some words that is present in that block, and that block is present in our cache. Then the cache hit occurred. That means cache hits occurred. But if the tag and the tag of the CPU generated address and the tag of the cache, the tag bits that is present in the cache is not matched, that means the CPU is wanting that particular block is not present in this moment in our cache. So then that time we called as a cache miss. That means we called it as a cache miss because that particular word CPU wants, it is not present in our cache at that particular moment. Then what we have to do? The cache miss occurred, and we have to move the particular block which CPU required. We have to move that block from the main memory to the cache, because that particular block is not present at this moment in our cache. So we have to move or transfer that block from the main memory to cache, and then again we have to check, and if it is matched, then we can say the cache miss cache miss has reduced and the cache is occurred. So if cache miss occurred, then that means we have to replace that block from the RAM, that's our main memory, to the cache. So this method, if you see, it is very simple, and searching is easy, because if 2 tag bits are compared, after comparing the 2 tag bits, if it is matched, then we can say that the block is particularly present in the cache, and we can say cache hit occurred. But if they are not two tag bits are not matched, then that means that particular moment the block is not present. So we have to transfer that block from RAM to the cache. This is what, that's why it is called, the method is simple and the searching is easy. Okay, clear? It is clear till now?
Yes.
So this is the advantage, that means direct mapping. This is the advantage of the direct mapping. But there is also, it is the advantage, but there is also the disadvantage present. What is the disadvantage? Now let's say in our block, this is our cache, and this cache, there is the 4 lines from L0, L1, L2, L3. Now we have specified through k mod n formula that B1, B5, Bn, then B9, then we can say B13, then B17. This all blocks should be present in the line number 0. So let's say CPU required a block that is B5 block. Let's say this is our cache. As we are taking the example, this is our cache, let's say, and this cache is divided into 4 lines, that from L0, L1, L2, and L3. Now we have a block that is present there. It is line number 1, that is block number 1 present. In line number 0, block number 0 will be present. Line number 2, block number 2 is present, and line number 3, the block number 3 is present. Okay, so that means at a particular moment a block is present there. So now let's say CPU requires block number 5. CPU requires, let's say not this is what, now this block number 5 is required now. So that means first block number 5 will go where? Block number 5 will be, if we use the formula k mod n, then 5 mod 4. So our answer will be 1. That means block 5 will be go to the line number 1. Line number 1, the block 5 will go. Now let's say after executing the block number 3, it is executed, and now there is line number 3 is our ideal. That means no block is present in this at this particular moment in the line number 3. Then again in the next case, let's say so that means what, after executing P1, block 5 will be present there, because at a particular moment one block should be present. Now let's say after that again CPU required, after some time CPU required block number 1 again for its another things execution, block number 1 again. Now we have already executed the block number 1 using the block number 1, and after finishing our task, it is again after finishing our task, this block number 1 we transferred it into the main memory again, because we have the CPU has performed its work. So that's why this block number 1 is transferred again to the main memory. Now the after executing the B5, let's say CPU required for another block, for again the block number 1 is required. Again the block number is required for its another execution. Now where this block number 1 will go? Now if we use the formula, because in direct mapping this formula is used k mod n, so that means block number 1 will have to came in the line number 1 only. Other than that it will not come. But you see, we have already in the line number 3 there is no block is present. There is no block present in the line number 3. So if we take this, then we can place it in the block number 1 in the line number 3. But in direct mapping this cannot be done, because in direct mapping this formula specified that block number 1 should be present in the line number 1, should be present in the line number 1. But we cannot place this block number 1 in the line number 3. So if that's why this is ideal, that means no block is present in this particular moment. And but also here no block is present, but we cannot accommodate that block in the line number 3, because block number 1 will came only in the line number 1. Other than that it will not came. So that's why we have to wait for some time. We have to wait some time that the execution or the execution required for block number 5 is completed, and after that it will be transferred to the main memory. Then only what, block number 1 we use, then only we will again transfer that block number 1 to the line number 1. But if this problem is, this formula is not specified, then we can already accommodate the block number 1 here, then we can execute that particular movement, but it is not possible due to this direct mapping. So this is a problem, this is the disadvantage. And another disadvantage is what, let's say we have to replace that block, that b5, when b5 comes, we have to replace that block number 1, because we have to accommodate this block number 1 here. So that's why we replace the block number 1. But if we use that block number 5 any other place, in any other place, then this block number 1 will be present in the particular cache all the time. So that's why the cache, if CPU checks, the tag bit is compared and the block will be present at particular moment in the block. So we can say that cache hit occurred. But here this is what, this is occurring the cache miss, because block is not present in that particular line at the moment. So assume, so that's why it is said that if we assume that CPU needed, if we see this, that B1, B5, Bn, observe executing, again B1 has to be used. B1 has to be used. So assume that after, if you see this example, that in line number 1 B5 came, after it's we B5 came, then B9 came, and after that again B1 is required. Now we have to accommodate B5, that's why B1 is replaced. To accommodate B9, we have to replace the B5 again. And now that's why assume that the CPU needed B1 again. But why B1 is not present at that particular moment is in the cache? Because it is replaced. So we have to brought that B1 from the RAM again. And so number of miss that it occurs. But if we have do not some position fixed issues, then our cache miss will position fixed issues, then our cache miss decreases. That means it will be what, the if some position fixed issues is not present, then the cache hit will be increased, because if there is the position fixed issue, and that's why we cannot accommodate. If other places are vacant, then also that means here, if let's say we can first B1 came, so we use B1 here, then B5 came. Now B5 we cannot place any other block, only in the line number 1 we can place the B5. So to place the B5, we have to do what? To place the B5, we have to replace this block number 1. But if let's say there is no position fixed issues, and B5 came, we place this B5 here, then B9 came, we place B9 here, and let's say after that B9 here, and after that let's say B1 is again required. In that time, when CPU will be checked, in that time the tag bit will be matched, and it find that the B1 is present in the L1 line. So directly we can say cache hit increases, but there is a position fixed issue. So that's why B5, B9 all should be present in the line number 1. And at a particular moment, what is that? At a particular moment, we can place in here only one block. So that's why we have to replace the B1 block. And that's why again the B1 is required. In that time, the B1 is not present in the line number 1. So that's why we have to again move that B1 into the line number 1 to accommodate that. So here it means that the in particular moment the block is not present in the cache. So that means we can say that is the cache miss. So this is the position fixed issue, and that's why the problem is generated. We called it as the conflict miss. The problem generated, this problem we call the conflict miss, and this is the disadvantage. So this is the disadvantage of the direct mapping technique. Okay, clear?
Yes, sir.
समझ में आया?
Yes, sir.
So this is the problem of the direct mapping. Now to overcome this problem, we use the fully associative mapping. The next type, the second type, that is the fully associative mapping. Now in this fully associative mapping, so I have taken the same example. You see, I have taken the same example which we have used in the direct mapping. That here 128 words is present. That means this our RAM is of 128 words, and this is what this 128 words, and each words in, we can say, in each block we can use the 4 words. In each block 4 words can be present. So that means 128 divided by 4, that means how many blocks should be present? 32 blocks should be present. So same, the same we have taken is here also, the same example we have taken. And in the cache we use, this cache is capable of storing 16 words. This cache is capable of storing 16 words, and that means each line, we can say each line will be storing a particular block. So that means the line size and the block size is equal. That means in line also, at a particular moment 4 words should be present. Now this 4 words is what? These 4 words will be for a single block. So that's why we say in a line at a particular moment 1 block should be present. So 16 divided by 4, that means total 4 lines should be present. So this is also the 4 line present here. Now the difference is what? In that time we use k mod n formula. So we use k mod n formula, and this formula represent that which block should go to which number line. This specifies that which block should go to the which line of the cache. But in the fully associative, and we have seen this position fixed issue see there, so that's why this is the disadvantage, the conflict miss occurred. So in fully associative there is no concept of this like k mod n formula. That means any block can go to anywhere. That means this block 0, this block 0 can be present in line number 0, this block can be present in line number 1, this block can be present in line number 2, this block can be present in line number 0 also. Same as that b1 can be in line number 0, b1 can be in line number 1, b1 can be in line number 2, b1 can be line number 3. But in the direct mapping b1 it should be present in the line number 1, because if we use that formula then k is what? The block number. So 1 mod 4, our result will be 1. That means what? That means the block number 1 should be present in the line number 1. But there is, in the fully associative mapping, there is no such constraint. There is no such constraints present. So any block can be present in any line. There is no such constraint. So that's why any block can be present in the any line. So that's why when the physical address will be generated, the physical address of this is the same physical address, because here we have seen that the physical address is of what? So 128 words. That means to represent 128 words 2 to the power 7, so 7 bits will be required to represent 128 words, and it will be divided into 2 parts. One is block number and another one is the block offset. Block offset means how many words can be present in the particular block, how many words can be present in the particular block. So in the block we have seen 4 words can be present. So to accommodate the 4 words 2 bits is required. 2 to the power 2, that means 2 bits is required. So block offset will be 2 bits, and the block number is what? Block number will be 7 minus 2, that is the 5 bits. So same as that in the direct mapping, which physical address of the RAM we have seen, or the main memory we have seen, same physical address is also present here. So that's why it is what? The same physical address, same bit physical address. And here you see there is no such cache address, because here we do not have fixed line issues. So if we do not have fixed line issues, any block can be present in any of the line. So that's why this address, this same address, because line number, but line number concept came where? The line number concept comes because in that time block number is this particular block number should be present in that line, this block is present in that line. We are specifying that, but here any block can be present in anywhere. So the concept of that address is not present here. The same way here it can be searched. So this block number, in that case, this block number for cache, this block number will be used as the tag in case of fully associative mapping. This block number, instead of this block number, you will use that tag number and then block offset. No such concept of line number will be there for if our address is of the cache. If CPU generate an address that is the cache associative, so in that case there will be no such concept. That in the previously we have seen, we have divided this block number into two parts. One is tag, another one is the line number. But here there is no such concept of the line number, because any block can be present in any line. Any block can be present in any line. So that's why this block number will be replaced as the tag number. So here in this case it will be tag number and block offset. So tag number of 5 bits tag and 2 bits block offset. So this will be like this for the our fully associative mapping. So that's why this is advantage is what. Now what is the advantage of this? Now the disadvantage which is occurring for the direct mapping, this is the advantage of this fully associative mapping, because in disadvantage of direct mapping we have seen that conflicts may occur due to the fixed position issues, but here there is no fixed position like issues, so conflict miss didn't occur here. So the location is not fixed, block can go to any line number, which is not applicable in the direct mapping. So this is what in direct mapping we divided into here tag, line number, block offset. But in this case this total will be our this tag and line number, this total will be our tag and this will be the block offset. So tag describes what it will be, which block is present at that particular time in the following position. In the following position, which block is present. Let's say now our tag length is what? Tag length is 5 bit and the block offset, our block offset is 2 bits. This is the thing. So let's say they are in a cache. In our cache, let's say the tag that is used in the cache, it is 00100. And let's say CPU generated address, the CPU generates an address, so the tag is compared. The tag is compared and the particular before, this particular before is what? This particular before is present in that moment, is present in that moment in the line number. So that means tag is compared. So if tag is matched, that means CPU will search where? CPU will search that particular block in the cache. So because if this tag is matched, then that means that particular block is present in our cache. So if CPU finds that particular block in our cache, that means we can say cache hit occurred. So to represent that, now this is what we have 4 lines. We have 4 lines. So that means how will we represent here? It will be 0 0, then 0 1, then 1 0, then 1 1. So this word number 16, word numbers, if we combine this, then it will form word number 16, word number 17, word number 18 and word number 19. This will be presented. So that's how the address will be generated here. The address, it will generate like this. So this is the advantage. This is the advantage of using the fully associative mapping. This is the advantage. So if we make the combination using the 4 bits, So we know using 4 bits how many combinations we can done. 00011011. Now the tag will be same. Here you see the tag is same 00100, same as this tag. The tag is same. And how many we can say that 4 combination we can form, that is 0001 1011. And if we place the same tag here, then which word it will from? This word, this will be the word number 16. This will from word number 17. This will from word number 18. This will from word number 19. So that means how many will be here? The word number 16, word number 17, word number 18, and word number 19. So in which block this is present? So if we use here, if we use, then word number 12, 13, 14, 15, it is present in B3. So 16, 17, 18, 19, it will be present in the block number 4. This will be present in the block number 4. So the block number 4 will what? This block number 4 we can present in the any number of line. So that means the cache hit occurred because the particular block CPU wants to find, it is present in the particular moment at that particular line. Or any of the, we can not particular line, we can say that it is present in the cache. Because why we will not use that particular line concept? Because in fully associative, the block can be present in any line, any of the line the block can be present. So we will not use that concept. So here, this is the thing, this is the thing, that this bits will be, or we can say this block is present in the cache. So we will find it like this. Okay, it is clear?
Yes,
समझ में
sir.
आया सबको? Okay. Now there is also a disadvantage. The disadvantage is what? Now size of the tag bit is what? The size of the tag bit increases. Now in direct mapping, if you see in the direct mapping, our size of the tag bit is what? Our size of the tag bit in that time, it was 3 bits. But in the fully associative mapping, our tag bit is of 5 bits. So here the tag bit is our 3 bits, but here the tag bit converted to the 5 bits. That means the size of the tag bit is increased here. So this is one disadvantage. And another disadvantage is what? The number of comparison increases. Or because of the number of tags, the number of comparison increases. Now, why the number of comparison increases? Now, in the direct mapping, the particular B, let's say the particular B1 block, this particular B1 block should be present in the line number 1